but we're very pleased today to have Thomas Koberda of the University of Virginia.
Right. Thank you, Catherine. Thank you all for coming. It's my first time to the IAS, so it's a pleasure to be here. All right, so I'm going to talk about homeomorphism groups of compact manifolds. So we'll let M be a topological manifold. So when I say topological, I mean that unless I really say otherwise, I don't assume that it has a smooth structure or PL structure, or even that it's homeomorphic to a simplicial complex or anything. I'll always assume that it's compact, unless I say otherwise. There will be one point later where I put it non-compact manifolds and connected, possibly with non-empty boundary. And I'm interested in the groups homeo of M, and inside of here, the group homeo 0 of M. So homeo of M here is the group of all homeomorphisms of M, and this group viewed with the compact open topology may not be connected. Okay, so then homeo 0 is the subgroup that consists of the connected component of the identity. So most of the things that I say in this talk will apply equally to homeo and homeo 0, so I won't really be paying too much attention to whether or not I write the subscript 0 or not. But the particular sorts of questions that I'm going to be interested in are, so for instance, what is the structure of maybe generally countable torsion-free subgroups of homeo. Sort of a second question, which could be thought of as, one prime, really, is to what degree do subgroups, ideally countable ones, sort of homeo 0 M, determine M, whatever that means. It's not a precisely phrased mathematical question. And the third general question is, what is the complexity of subgroups of homeo 0 of M? So sufficiently complicated ones or something like that. In any case, these statements that are not particularly precise here, I will try and make a little bit more precise and explicit as I continue. Okay, great. So maybe the first thing I'll do is address sort of this first question about the group itself and to what degree the underlying manifold is recovered. So, I mean, this can also, if you let in this case maybe G here in question 2, which I said was 1 prime, when G is the full group homeo 0 of M, you can think of this yet from another perspective, like you have some sort of object in a category, like in this case, you have the manifold, which is an object in this topological category, and it has some automorphism group. Okay. And so to what degree does knowing that automorphism group and what it is recover for you what that object was? Okay, so that's maybe where we'll start.
That's kind of step 0 before you start asking about subgroups.
Yes, yes. Okay. Well, it'll take a while before I actually get to subgroups. Yeah. Okay. But step 0 is, I think, a good place to enter. Right. So here's a theorem due to Whitaker from, I think, 1969. Okay, so he said the following: so let M and N be compact manifolds. So then he says, so let phi just be an isomorphism between their homeomorphism groups. So let phi be an isomorphism between homeo 0 of M and homeo 0 of N. So here, really, I just mean a abstract isomorphism of groups, so nothing else is assumed. So then there exists a homeomorphism F from M to N, such that, well, if you apply phi to an element of homeo 0 of M, you'd better get an element of homeo 0 of M. So if we do that, well, we can get an element of homeo 0 of N by applying F inverse first, and then G, and then F. So, right, so the theorem is that any abstract isomorphism between two homeomorphism groups of manifolds, even their identity components, is automatically induced by conjugation by a homeomorphism between the underlying manifolds. Okay, great. So that has sort of a lot of immediate consequences. For instance, if you want to know what's the outer automorphism group of, say, homeo 0 of M, right? So then you have, this gives you the answer immediately, and you just take the full group of homeomorphisms quotient out by the identity components. So this is like the mapping class group, or the topological mapping class group. So usually there's some issue, especially in higher dimension, between smooth mapping class groups and topological mapping class groups. But in any case, that's what you get. And it seems to sort of just answer completely the question in the step 0 case, where G is equal to homeo 0 of M, right? The isomorphism type of this group determines it, determines the underlying manifold completely. And it turns out, I'll just say as a side remark, I said at the very beginning that M was a topological manifold, so we need not assume anything about its underlying structure. But there are corresponding results that are also true for smooth manifolds. So there's a bunch of names associated to this. Takens, Filipkiewicz, Bacher, Montgomery, Epstein, Ling. So what they say is, like, okay, consider M and N smooth compact manifolds. Right, and suppose you have an abstract isomorphism of groups between, say, diff K of M, even diff K 0 is fine, and diff L 0 of N, where here K and L are integers. positive integers in any case. Then K is equal to L and phi is induced by a CK diffeomorphism. So the exact analog of Whitaker's theorem, except in the smooth case. I'm not gonna, actually, you can actually allow this to be infinity, by the way, right? So this could be stated like this, and I'm not gonna say too much about this. We can talk for a very, very long time about smoothability and the various issues that arise there.
So what do you assume about phi?
It's just an isomorphism of groups,
Like completely abstract?
abstract.
Not
It doesn't have to be, the continuity is automatic, it turns out, yeah.
That's why I was asking about step 0. It's step 0 tells you once you know isomorphism of one set of groups, now you know thing on the manifolds. And questions 1, 2, and 3 are more like, what's the group structure of homeo 0? Can you recover the group from its subgroups?
Yes,
Which is almost a purely group theoretic question.
yes.
At least-
That's what I will be
Okay, great.
investigating more and or giving ways to investigate it and talk about complexity. Great. Right, so so both of these theorems are sort of open and shut cases, right? In the sense that there's somehow no more to say about the isomorphism type of these groups. I personally don't like the setup of saying like here's an abstract isomorphism between these two groups, because I sort of like I like my mathematics more concrete. I like to be able to hold one of these maps in my hand, and you cannot, because these are very large groups. I mean, sort of a posteriori that okay, this very, very large isomorphism between very large groups comes from something which is maybe slightly more explicit, but only somewhat more explicit. I'm not so sure what is meant to say like here is a homeomorphism, because that's not really a finite piece of data in any sense, or even a computable piece of data in any sense. So what I'd like to do first is to give step 0.5 will be to give a more concrete understanding of Whitaker's theory. And so that's where so some model theory will come in. So I'd like to talk about the first order theory of homeo 0 of n. So let me explain a little bit what these things are, right? So the theory, so these are supposed to be, I'll use this shorthand, theory of homeo 0 of m. These are the sentences, so formal sentences in the language of group theory that are true in homeo 0 of m. Okay, so what are formal sentences? Right, so these are formal strings of symbols which are allowed to be the following. So you have some non-logical symbols and some logical symbols. Right, so the non-logical symbols will be this binary operation, which is usually just the multiplication inside of the group. Okay, and you have also the identity element, so this constant, which is usually interpreted as such, right? And then there are logical symbols, and, or, implies, not, equals, for all, there exists, and some countable list of variables. Okay, so now what is allowed to be a formal sentence and sort of what first order mean are somehow closely related, right? So the first order here is telling you what these variables are allowed to mean. Okay, so these variables are only allowed to refer to elements inside of homeo 0 of M as opposed to subsets or subsets of Cartesian products or anything like that. So that's where in first order logic, right? So you interrogate structures about their constituent elements and not about their subsets. That the reason for doing that is, well, because if you talk about something like second order logic where you have subsets, then there's some philosophical disagreement about what that can mean. Right? So you have to, when you have arbitrary subsets, you have to specify what the semantics of your logic are. And as far as most people are concerned, what an element is and what it isn't is not so much up for debate. Okay, so then to give a fully precise definition of what a formal sentence is going to be, I mean, I'd have to give some sort of inductive definition, which I won't, but I think just one example will be good enough. So for instance, the following: for all x1, for all x2, x1 times x2 is equal to x2 times x1. Okay, this is some sentence phi, call it phi ab, right? So that is a perfectly good sentence that I've written in the language of group theory, okay? And we see that phi ab is in the theory of some group G if and only if G is abelian. Great. So what's not an example would be something like, well, you start saying for all subgroups, or there exists a homomorphism. Right, so both of these are not allowed. Up the order, please. Okay. Great. So this is what I mean when I say first order formulae or sentences. Okay. And then if you have a particular first order sentence in the language of group theory, okay, then you have an actual group. This sentence may or may not be true in that group, okay? And if it is true, then it's a member of the theory of that group, and otherwise it's not. So that's what I mean here when I say the theory of homeo 0 of M, a set of sentences in the language of group theory that are true in homeo of M. So then you can say the following, right? So G is 3 lines H. So this means elementarily equivalent. So two groups are elementarily equivalent by definition if the theory of G is equal to the theory of H. Okay, so this is some sort of equivalence relation that you can put on groups, which is a natural equivalence relation that one uses in model theory if one is now treating the theory of an object versus as opposed to the object itself as the mathematical object of interest. Okay, so it's clear that if two groups are isomorphic to each other, then they're elementarily equivalent, as you take any sentence in one and then you can transport it by an isomorphism and get witnesses for one sentence here to get witnesses for that same sentence in the other. Okay, that's straightforward. The converse is not true, right? So there's any two non-abelian free groups are elementarily equivalent. That's the theorem of Sela, Harlampovich, and Myasnikov. Okay, so this is a strictly coarser equivalence relation than isomorphism. Okay, so why have I brought all this up? Well, I said that I was going to try and get a more concrete understanding of this theorem, okay? And it'll secretly also play into my original questions here, so that will be clear in just a moment, I hope. Okay, so what can we do with all this? So here's a theorem due to Kim Kardashian and Javier de la Nuez Gonzalez. So if M and N are compact connected manifolds, then there exists a sentence phi sub M, okay, in the theory of homeo zero of M, such that phi sub M is in the theory of homeo zero of N, if and only if M and N are homeomorphic to each other as manifolds. So, great. So that's the sort of first theorem. This is what I would call maybe a syntactic version of Whitaker's theorem. So what this is saying now is that there's some string, a single one suffices, of symbols, right, that forms a sentence in the theory of groups, which nails down the homeomorphism group of your favorite manifold. So among all homeomorphism groups of all manifolds, there's a way that is in principle possible to write down, which nails it down. And it is possible really to write it down, especially in dimension one. You can write it down pretty explicitly. You could probably do it in half a page. If you had a manifold of dimension 2 or more, you'd be able to write it down probably within 10 pages. If you had a reasonably explicit embedding of that manifold into Euclidean space.
What is it for the circle?
So for the circle, so you have to use the fact that sort of these regular open subsets of the manifold are interpretable within the group theory. And so there's some sort of a definable equivalence relation on group elements, which spits out that two group elements are equivalent if and only if their extended supports are equal. So that's to say the interior of the closure of the points that they don't fix. Okay, and so then those form a Boolean algebra. Okay, and that Boolean algebra has these Boolean operations like join, meet, supremum, infimum, complement. And so what then you can do is you can express some of the topological properties of this Boolean algebra because you have a group acting on it as well. And so you can say, look, for every regular open set that has two components, its Boolean complement has at least two components. That characterizes the circle up to homeomorphism among all manifolds, in fact. And for the interval, it's actually that as long as you have, whenever you have one component that's not sort of accumulating on the boundary, its Boolean complement has at least two components in it. That characterizes the interval among all manifolds. This is using the one dimensionality in a very, in a very essential way. And that's why I said for in dimensions 2 and higher, like you have to have some sort of reasonably explicit embedding into Euclidean space to be able to do anything. It's much, much, much more complicated in that case.
How easy is it to check if phi m lies in the theory of sorry.
Yeah. Getting
You're
there.
just pushing the difficulty somewhere else.
Oh, yeah, we absolutely are pushing this, and you have, and it's going to be very, very, very difficult. Okay. Great. So in any case, there is such a description, right? There's a description that works for every manifold, and one can, in principle, write it down. Okay, so how can you check if two manifolds are not homeomorphic, or in general, what does this have to do with the original questions that I asked? Okay. So right, so now we have this group, okay, the homeomorphism group of M. Right, so I also asked how complicated can homeo zero of M and maybe its subgroups be? Okay. So that's a very difficult question to answer, sort of to phrase in a way that makes sense mathematically and isn't somehow trivial. Right? Because if I give you a homeomorphism group of one manifold and of another manifold, how would you compare them? Well, normally you'd have to find a map between them. And generally, there are going to be no maps that are non-trivial between these homeomorphism groups. Usually, these groups are usually simple, right? So maps are usually going to be isomorphisms to their image. So usually that comes from a topological map between the underlying manifolds, or it just is the trivial map. So there's just no way to compare these things very efficiently. But now that we have this model theoretic perspective, we can talk about the whole theory of the homeomorphism group as a measure of complexity. So what do I mean by that? Well, the theory of any structure over any language, maybe a finite language, let's say, can be embedded as a subset of the natural numbers via one of these Gödel encodings. Okay, so what do I mean by that? So this is the same thing that one uses in computability theory, right? So you have this universal this universal Turing machine that takes as an input an index, and then it decodes that into a program and then evaluates it on various inputs. Okay, this is exactly the same idea. How do you encode a program as a natural number? Well, you can take all of these logical and non-logical symbols and you assign them numbers, unique numbers. Maybe everything but the variables are given some even indices, and the variables are given odd indices. And then if you have a well-formed formula or sentence in this language, then you can encode it by taking the first prime number to the power of the first index times the second prime number to the power of the second index, and so on. And then you get this product of prime numbers, okay, it's some natural number, okay? And now you've encoded that particular formula in a unique way as a natural number, because you take a natural number, you factor it, and most of the time you'll get nonsense, but you can check if you get nonsense, then you just ignore it, right? If you get something that's sensical, then you've, in a unique way, gotten a string of these logical and non-logical symbols, which is a sentence which means something, right? And so, in that sense, I've replaced this very, very big, uncountable group, the homeomorphism group, with a countable thing, which is the subset of the natural numbers, and its elements really are just like natural numbers, things that we're used to dealing with. Okay. Great. So, okay, now we have the natural numbers, okay, and some subset of them. So how complicated is it? Now, this is now a much more natural question to ask from the point of view of, say, computability, because if you have some subset of the natural numbers, you ask things like, well, is there a Turing machine that computes it? Or maybe is it at least recursively enumerable? Or is it arithmetic? That is to say, is it defined by some formula in the first order theory of arithmetic, which is to say, you have addition and multiplication of the successor in the order, right? And some sentence, some formula defines this subset. Well, it's bad news. So here's a fact that there's the membership in theory of homeo of M, homeo zero of M, viewed as a subset of the natural numbers, is undecidable in ZFC. So what I mean precisely by this is that there is a particular natural number that you can write down, and whether or not it is I mean, you probably can't actually write it down, but it's in principle where you can write it down. Whether or not it is an element of whether it's encoding an element of theory of homeo zero of M or not, is equivalent to, say, ZFC being consistent, right? So it may be, I mean, I don't know, the homeomorphism of M that I look at is the same one as the one that you look at, only insofar as we've axiomatized mathematics consistently, right? So you cannot prove within ZFC that some particular natural number is an element of this theory. So that's kind of bad, but oh well. This isn't the only place where sort of set theoretic issues in a serious way come up. And so I said at the very beginning that I'm generally going to assume compactness of the manifolds, but let's just open this sort of closet door and see what happens if we have non-compact manifolds for a moment. Okay, so here's a theorem that's due to Hansen, this person, Nuez Gonzalez, and Rosendahl.
Their name is Kardashian.
Just
In case you forgot.
Just Kardashian, thank you. So we can sort of ask the same question that we answered here for non-compact manifolds. Is it true that if you have two homeomorphism groups of arbitrary, say, non-compact manifolds with boundary, and they have their first order theories are the same, are the homeomorphism groups isomorphic? That is, say, are really the manifolds homeomorphic to each other? Okay, maybe. Well, it's a very big maybe. So the theorem is that for non-compact M and N with the boundary of M equal to the boundary of N equal to the empty set, we have the following: if V equals L, so I'll explain what that is in just a second, then elementary equivalence implies is equivalent to homeomorphism of the underlying manifolds. So V equals L is something called Gödel constructibility. So this is an assumption about the set theoretic universe that you use. Okay, so when you build up sets in this von Neumann hierarchy, right? So you start with the empty set and you keep taking your sort of the power set, and then you build up bigger and bigger things. Okay. So what Gödel constructibility is about, it says that, okay, well, the power set, that's the controversial axiom here. We have to agree on what we mean by subset. And the constructibility hypothesis here says that the things that are the things that are definable. So you've restricted the power set to the sets that are definable somehow in the language of set theory from things below. Okay, so what that means in practice is that you have somehow the smallest possible model of set theory. Okay, and so the point of building that universe was to prove that, that the continuum hypothesis, for example, is consistent with ZFC. In fact, the axiom of choice plus is a consequence of V equals L together with ZF. But anyway, so if you assume V equals L, then also two elementarily equivalent homeomorphism groups of manifolds come from homeomorphic underlying manifolds. And on the other hand, if something called PD holds, then there exists M and N such that M is not homeomorphic to N. And the theory of the homeomorphism group of one is equal to the theory of the homeomorphism group of the other. Okay, so this PD is something called projective determinacy, and this is some different strengthening of ZFC, which has to do with certain games. All of determinacy is about playing certain games and being able to win them when you play them in bare space. In any case, I won't get into the details of what this means, but the point is that depending on which strengthening of ZFC you take, the answers are different. Okay, so this is maybe then not so strange that the membership inside of the theory of a homeomorphism group depends on a strengthening of ZFC that you take. Okay, great. So let's maybe return to Earth a little bit and talk about some maybe simpler subgroups where we can still get sort of the strength of being able to recover the underlying manifold and talk about the complexity, that the complexity is not so incredibly complicated that there's nothing that we can do.
Sorry, so this part 2 doesn't contradict your theorem because the theorem used the compactness, the fact that there's no bound.
These are definitely only for non-compact. These are only non-compact examples.
How you use the boundary to construct these M and N's.
So these don't have boundary, right? So these are usually
Okay.
these are usually like very, very wild at infinity manifolds. So things like, you think of some surface with like a Cantor set missing or something like that. These are pretty wild things. Great. Okay. So for the remainder of the talk, I'll talk about something called Rubin's theory and the first order version of it. Okay, so Rubin sort of had this general program, which I alluded to earlier, that if you have some object in some category, it's automorphism group. You want to recover that object back. So what can you do with that in the topological category? So let's just say he has X, locally compact Hausdorff topological space. Okay, and you take G, a subset of homogeneous X. Okay, so you'd like to say that, well, G should determine X somehow, but of course, a general G won't do it. You need to put some assumptions on it. So there's some definitions here which are a little bit maybe hard to process on the first view, but I'll try and explain them a little bit, right? So generally here, I will write the following. So U inside of X will always be a non-empty open set, okay? And G brackets U, this is called the rigid stabilizer. The rigid stabilizer of U, and this is a subgroup of G, and this simply consists of elements G such that G of X is equal to X for all X not in U. Okay, so it's just the stuff that's the identity outside of big U. Okay, so G is locally moving if for all U, GU is not the trivial group. Okay, so and the second is G is locally dense if for all U and for all P in U, if we look at the orbit of P under the rigid stabilizer of U and take its closure, this has non-empty interior. Okay. So, right, so this is saying here that if you look at any open set, you can find things that are the identity everywhere outside of this local thing, and that do something non-trivial here. And this one is saying that, well, not only that, your orbit isn't like a Cantor set or something like this. And it may seem that this is strictly weaker than that, but that's not always true. If you have a manifold with boundary, for example, then you can have a locally moving, the whole homeomorphism group is locally moving, but it's not locally dense in this sense. Because if you have a point on the boundary, no matter what you do, it stays in the boundary, so its orbit doesn't have any interior. But that's okay. That's just maybe not always the best definition in that particular case. And one more definition that I give, which I'll give, which only applies to manifolds. Here, when X is a manifold. So then for all U, an open colored ball, that is to say, U is the interior of a closed ball inside of M, which can be extended to a ball of larger radius. So it's not like a weirdly embedded ball that's sort of going all over the place. Okay, then we assume that the I should have a name here. So G is locally approximating if the rigid stabilizer of U is dense in the full rigid stabilizer of that open set inside of homeo M of U. So that's in the compact open topology. So that's to say, right, if you have this small open ball, right, then if you're locally approximating, that means that any homeomorphism of the manifold that's supported only in this open set can be approximated as well as you want in the compact open topology by an element of G. Okay. Great. So these may seem pretty strange as conditions to put. Well, I mean, they occur naturally. I mean, homeomorphism groups of manifolds are always locally moving, right? They're locally dense in the appropriate sense, at least when M is closed. And if you have boundary, then you're locally dense in the interior and also on the boundary separately. And you're always locally approximating. And you have plenty of countable groups which have these properties. Because you can take, a countable basis for the topology, and then for every open set in that countable basis, you just take some dense subgroup of that rigid stabilizer inside of the whole homeomorphism group, which can be taken to be countable, right? And then you just take the subgroup generated by all of those. So there are plenty of countable examples here. That's something. Great. So why do we care? So Rubin's theorem says that if G is a subgroup of two homeomorphism groups, homeo of X and homeo of Y, and it's locally dense for both, then X is is homeomorphic to Y in a G equivariant way. So because I'm running a little bit short on time, I won't write out all the words. What I mean there is that if G acts on X and an X acts on Y, and those actions are locally dense, then there is a homeomorphism from X to Y that intertwines those actions of G. That means, in other words, that G simply encodes all of the topology of X entirely within its group theory. So that's something. Okay, so I already made an allusion to the first step. I mean, step one of how that proof works when I said that you can interpret the regular open sets inside of G. That already is something that comes from just being locally moving, it turns out. But you can do much more if you so the way that you do this is you encode points somehow. And Well, a point is going to be just some descending sequence of open sets which have compact closure in one in the previous one, and then they have to be sort of shrinking fast enough, and then their intersection is going to be the point, and then that's being able to identify when you reconstruct a point is the key. And once you've done that, you're done. You know how to prove the theorem. By the way, if we go back to this smooth version of Whitaker's theorem, Rubin's theorem gives you a place to start because these groups are locally dense, acting on at least in the case where the manifolds are closed, right? So if you have this isomorphism between two diffeomorphism groups, right, then there is a homeomorphism between M and N, which intertwines the two actions, right? So at least you have some place to start. You have to do a lot of work to promote that homeomorphism to a diffeomorphism, right? But at least you know that the underlying manifolds had to be homeomorphic at least. Great. Right, so that's Rubin's theorem. Okay, so what can we do, with the first order version? So here, this theorem was a first order version of Whitaker's theorem, right? And because Whitaker's theorem is definitely not using the first order theory you're building, again, you basically have to build sort of ultra filters inside of the group to be able to reconstruct points, and that's exactly what Rubin does here. Okay, so that's not a first order thing. So what can we do? Because in the theorem here, says the following. So suppose M is triangulable and closed. Okay, so it's a closed manifold that is homeomorphic to a simplicial complex. And so the following, one is G, a subgroup of homeo 0 of M, which is locally approximating. Right? And you need a group H, which is elementarily equivalent to G. And third, H should be a subgroup of some other manifold, homeo of N, which has no assumptions on it. Doesn't even have to be compact for this in this case, which is also, but H has to be locally approximating. Okay, so then M and N are homotopy equivalent. So this is not necessarily homomorphic, but homotopy equivalent was the best that we could do, at least for now. Okay, so let me say what the essential content here is. So the essential content is this point. H is only elementarily equivalent to G. Right. So if H and G were the same group up to isomorphism, and if H were then a locally approximating subgroup of homeo of N, then we would just apply Rubin's theorem to get the conclusion that M and N were homeomorphic to each other. But now there's no comparison map between H and G. They just have the same theory. So just from knowing that they have the same theory and that H is a subgroup of homeo 0 of N tells you that M and N have to be homotopy equivalent to each other. In dimensions 3 and lower, one can prove directly that M and N actually have to be homeomorphic in this case. And there are some cases in which you know that this thing called the Borel conjecture is true, which says that if you have two closed aspherical manifolds that are homotopy equivalent, and they should be homeomorphic to each other. I think it's believed by many, I'm not claiming to have a counterexample, but that it's false. The Borel conjecture is false in general, although it's known in many cases. Right, so in any case, we do get actual homeomorphism in many cases. Okay. Great, so that's, that's sort of giving some answer to 1 and 2 here. So in the remaining time, let me just say a few things returning to the complexity, right? So here we talked about the complexity of the full theory of the homeomorphism group, okay, and that's way too complicated. But what about the theory of some locally approximating groups? Well, clearly they can be very complicated already because, as we know, the whole homeomorphism group of M is locally approximating just by definition. But a good place to begin to get an idea of what could be true is to look at the group T, which is a subgroup of homeo 0 of S1. So this is Thompson's group T. So what this is you view the circle as the reals modulo the integers, okay? And then this gives you a piecewise linear structure on the circle. Okay, so now you can look at the piecewise linear homeomorphisms of the circle, which have, so a piecewise linear homeomorphism is going to be like smooth away from finitely many points. Okay, and at the points where it's not smooth, those points have to be dyadic rational numbers. Okay, and moreover, wherever you're smooth, the derivative has to be a constant power of 2. Okay, so that's the definition of Thompson's group T. So that's already quite a very digested definition. This actually comes from a question about logic instead of non-associative monoids. But monoids are associative by definition, non-associative semigroups. Anyway, so right, so the point is that this is now some subgroup of homeo 0 of the circle, right? Which, because of its very explicit definition, right? So if I wanted to specify for you an element of T, I would just hand you a finite list of dyadic rationals, right? And you would be able to reconstruct the homeomorphism completely. And if I gave you 2 of them, you would know how to compose them. And so what does that mean? That means that T is interpretable in arithmetic. So this phrase interpretable has a precise mathematical meaning. I'm not going to get into that, but the point is that if you know what the integers and addition and multiplication and the order are, right, then you can reconstruct this group T. You can sort of encode it as finite sequences of integers, right? And you can do the group multiplication as some definable function within arithmetic, and you can compute everything about this group. What's more is that, on the other hand, T interprets arithmetic. So what does that mean? Well, so what that means is that T, you can view it now as an abstract group, and so it's just a set with this binary operation on it that has these axioms of group theory that are satisfied. It turns out that just from that information, you can reconstruct the integers together with addition, multiplication, the order. So that means that these theories, you can say something slightly more, in that that arithmetic and the group theory of T are bi-interpretable. That is to say that they really have the exact same information inside of them. Okay. What's more is that T is actually dense in the whole homeomorphism group, and it's locally approximating. So T is something that falls under the general framework of everything I've been talking about up to now. And it gives a sense of what happens for a general locally approximating group. So here's a theorem, which is actually, really it's a lemma that goes into the proof of this theorem, which is that if G inside of homeo 0 of M is locally approximating, then G interprets arithmetic. Okay. So that means that really just from the group theory, just at the abstract group, you can do everything that you can do in arithmetic in that group already. And it actually, this interpretation doesn't depend on what M is. You can do it in, so if you ask this manifold and this locally approximating group what arithmetic is, and you ask this one over here, they would give you the same answer. You have the exact same definition. Okay, so what does this mean about complexity? Okay. So let's go back to Turing machines. Okay, so if you have a Turing machine that has sort of no external information, then you can ask, will a Turing machine with a particular index halt on a particular value, on a particular input? And then that defines for you some subset of the natural numbers, the values of the pairs index input on which the universal Turing machine halts. That's called the halting set. Okay, and that set itself is not computable by any Turing machine, by one of these sort of classical diagonalization arguments. Okay, so when you're talking now about subsets of the natural numbers, which are, and you view them as computable things, okay, then you can look at all subsets of the natural numbers which are computed by Turing machines, and you know that's not everything because you have this halting set. So the things that are computable by a Turing machine are the yellow will be a boldface, right? So there's empty set is this class of subsets of the natural numbers which are computable. Okay, and these have a halting set. Right? And then if you look at the things which are now computable, if you have access to the halting set as an oracle, this is called Turing jump. So you can compute more things if you can say, well, did the no information Turing machine converge on this particular value? Okay. If you can ask a question like that at no cost, or a sort of one computational unit of cost, okay, then you get this larger collection of sets, which is this Turing jump. And you can, then this thing has its own halting set, and you can get the Turing jump of that, and you get, that's just empty set 2. And you can do this over and over and over. And you do this countably many times, and you get this Turing jump empty set omega. Okay, and this is what we could call Turing reducible to the full theory of the natural numbers. Okay, so there's a good reason why these are actually the same. But the point is that if you had some Gödel numbering for the theory of arithmetic, then the complexity of this set would be exactly the same as the computable things in empty set omega. Okay, and so just in the last 30 seconds, this theorem shows that the complexity of the theory of any locally approximating group of homeomorphisms is at least this. And it turns out that every Turing jump above this is populated by some locally approximating group of homeomorphisms. So there are a lot of them. I'll stop here.
Questions?
Ask a really stupid question. When you say T interprets arithmetic, or you can construct arithmetic from T, but I can construct arithmetic without T. I just need the empty set and and I can construct the natural numbers, and so what does it mean to use T to construct it?
But but you don't, so what is that predicate of when you take the power set, or in particular, this element is this symbol is an element of, so you don't know what T doesn't know what that is. It's just not part of T's language.
But you can construct it from T.
Right, so the point here is that, okay, so you only have access to the group multiplication and the identity element and sort of logical symbols, and you have to somehow pretend that this is like a field, right? And then you take an algebraic variety over that field, which is somehow like a definable set. And that needs to somehow be equal to the natural numbers. Right? And you have to have constructed the predicates that mean like this triple A, B, and C is in this relation plus if A plus B is equal to C, right? And so really what that means in some precise sense is that, right, so that there exists some X which is contained in some Cartesian power of maybe some definable subsets D inside of some Cartesian power of T modulo some definable equivalence relation. Okay, so you can think of this is really cutting out like an algebraic variety inside of T to the n if you pretended that T was a field, right? And then this is some definable equivalence relation, so it's like a projective space or something over T, right? And this has to be in some canonical way isomorphic to the natural numbers. And what's more is that, you know, all the symbols that the logical symbols that play a role in n, like addition and multiplication and the order, they have to be definable in X, but inside of here via the group theoretic information that you only have in T, right? So when you said start with the empty set and keep taking the power set, well, when you take the power set, you're implicitly using this symbol is an element of, and T doesn't know what this is. This is just not something that is part of the data that you're given. And so I think that's the answer. Yeah.
Other questions? Okay, should we leave the speaker again?